In this quiz, we were looking at predicting products of reactions as well as redox reactions. So here we're asking, well, what are the products for the following reactions? Basically, if I bring magnesium chloride and sodium hydroxide together, what do we get? And if we bring sulfuric acid and lead 4 hydroxide together, what do we get? And so for the first one, we want to look at this and say, well, both are ionic compounds. So I want to be thinking along the lines of double displacement. Both are binary ionic compounds, and so if they're both aqueous, the idea is that they're going to try to switch if in solution. And that's what we get, right? We have magnesium now pairs with hydroxide, sodium now pairs with chloride. This isn't balanced, but that's totally okay. We can see what the product is from this, both of the products. Second, we have the sulfuric acid with the lead 4 hydroxide. And in this case, they may both look like ionic compounds, but there's a few differences. First, that the lead hydroxide is solid to begin with. And second, that we don't have an ionic compound for our first reactant. We have the sulfuric acid. But still, we have what looks like a cation and an anion. And so trying to switch those is a good idea. And let's attempt that. We end up with water and lead sulfate, lead 4 sulfate. And this actually looks pretty good too, because this is really the type of reaction where we have an acid and we have a hydroxide. And so the acid is going to break down that hydroxide and it's going to leave a new compound, plus we'll have water as a neutral compound. So that's the answer for the first one. We want to make sure we remember our states of matter and that we're remembering our solubility rules. Second part is saying, well, how would we classify these reactions? And so we've talked about this a little bit already, but in the first case, we want to think double displacement. So I think that's a good way to classify it. And we could also call it a precipitation reaction, as we have two aqueous solutions coming together to form a solid precipitate. Now, what about the second? Do we want to classify this the same way? Could we say double displacement? I think we could. You know, we have a switching, so to speak, of the positively charged ion and the negatively charged one. But we don't want to call this a precipitation because there kind of is a solid already. It's not like two aqueous solutions coming together to make a solid product. But we do want to consider this an acid-base neutralization because we have the hydroxide and the H+, the proton from the acid, that are coming together to form water. Finally, we want to note that neither of these is a redox reaction. So as we look through redox reactions, we would see oxidation numbers changing. And this could be a good exercise for you to get all the oxidation numbers on these different atoms within these reactions. And what you should observe is that neither is going to be a redox reaction, as all the oxidation numbers will be exactly the same. And if you are able to show that they're all the same, that's really a good exercise. Okay, what about redox reactions specifically? Now we have two different redox reactions involving carbon and oxygen. And the first thing we want to do is we want to state the oxidation numbers for all of these atoms, which is going to help us determine, well, what's gaining electrons, what's losing electrons. That's really the heart of reduction oxidation, aka redox reactions. And so we have some rules that we've been practicing, and I want to just get the ones that fit with the rules first. So the first carbon in the top equation, I'm going to skip over because we don't know exactly what carbon's going to be. It's going to depend on the other stuff within that compound. But we do know that hydrogen in a compound likes to be +1, and so there's hydrogen +1 there. Oxygen, all by itself, wants to be 0. And note that the coefficients here, these equations are balanced, but these coefficients don't matter. If it's O2, it's always going to be 0 oxidation number. +1 for hydrogen again. Hydrogen likes to be +1 in a compound. And remember that oxygen likes to be 0 when it's by itself, but when it's in a compound, it likes to be -2. And that's going to be the same in the carbon dioxide as well. Other things to keep in mind, we're getting the number for the atom specifically, not the group. So if this is CO2, there are 2 oxygens there, that's true, but that each of those oxygens is -2. So the fact that there's 2 of them definitely matters, but we'd want to label just what the oxidation number is for that specific atom. And so that comes into play over here with the first carbon in the ethane, where the hydrogen is +6. Each brings 1 positive to the overall oxidation number, which needs to sum to 0 because it needs to add up to 0. It's a neutral molecule here. And in that case, the carbon has to be 3-. 2 carbons each at 3- bring -6. Each of the 6 hydrogens brings +1, so that's +6 total. And for the carbon and carbon dioxide, therefore that one needs to be +4. -2 for each oxygen, there are two of them, which makes +4 for the carbon. A lot of these are pretty much the same for the bottom equation, so I'm just going to go ahead and put those in. +1 for hydrogens in a compound, -2 for oxygens. Elements all by themselves are going to be always 0, and that's our rule so far. For the carbons here, we note that the carbon in the ethanol is -2. That's because we have -2 from the oxygen, +6 from the 6 hydrogens, and that leaves -4 that the carbons need to account for, which means each needs to be -2. And for the carbon dioxide, it's actually the same thing, still +4. If we have carbon dioxide here, carbon dioxide there, carbon dioxide anywhere, the oxidation number for the carbons and the oxygens are always going to be the same. Okay, for the final question, we're saying, well, what's oxygen doing in these reactions? And does this describe why we call losing electrons oxidation? And if we look, we see that in both cases, we have elemental oxygen that is reduced. Oxygen is actually gaining electrons, going from 0 to -2. 0 in the O2 on the reactant side to -2 in the CO2 on the product side. And therefore, we call it the oxidizing agent. Because it's reduced, it is promoting oxidation, causing things to be oxidized. And that's kind of why we call it oxidation. Elemental oxygen, oxygen in the air, it's very common. And when we leave things out in oxygen, there is a reaction where oxygen wants to pick up electrons, taking electrons for something else. And when it takes those electrons, we say that that thing has become oxidized.